wasn't changing slides for me.
Okay.
I don't know why.
You can progress forward by
But yeah, I was just using the
keyboard and outside
keyboard
choose the buttons.
Okay.
and the laser crystals.
Okay, guys, my name is Kevin Gima, and my first talk is going to be about charge transfer. So first, I'm going to be talking about the band out variable that we're using in our Matlab scripts. So basically, the band out variable, it's essentially an integration of the particle files down to 1 or 2 dimensions, and that integration we're using, it is like essentially a Fourier transform. So when we initially have these particle files, a lot of noise is mixed in with the actual data that we need. So to basically cancel out that noise, what we do is we essentially do a Fourier transform just to like take out or reduce the noise and to enhance the data that we're using. And then after that, we essentially plot our data. So this is the code we use in Matlab to plot everything, and the last 2 are the waterfall commands that we talked about.
Strive.
Yay. All right. So that's it for the.
The sensor is like behind you.
Your sensor is somewhere under the
Or
table.
behind is like
Under the table.
Pointed toward the computer.
180 degrees. So
Right here?
towards-
Yeah, somewhere there.
All right. All right. So let's finish talking about band out. So basically, when you plot, you get a graph with a time on the x-axis, and then degree of overlap between the 2 orbitals you're looking at. That goes on the y-axis. Matlab then takes the company files that you make in BOS, and it basically does an auto correlation. I don't know if you guys remember last week, but when David was presenting his talks on autocorrelation on his first slide, there was an integral equation that he put up there. That's essentially like what phosphate is doing when it's doing like autocorrelation, and that equation is essentially a Fourier transform.
Not fast. Matlab script.
Oh, Matlab. My mistake. So then, what essentially is happening? It's a graph that tells you how the correlation between the 2 orbitals varies in time, and then right here on the bottom, that's the code you use to essentially extract whatever data you need from the band out. So the BH is the variable that represents the electron hole, and the BE is the actual electron. Okay, so then what we have here are more graphs. Once again, we're using the waterfall command to plot everything. The X label is angstrom, which, as you guys know, is the unit that's used to measure interatomic distances. And then the y-axis right here, electron volts, that's the orbital energy. So what this graph is essentially telling you is how the orbital energy varies with distance.
It's distribution of density in space.
Okay, distribution of density in space.
What is the connection between the little image on the top, this one, and the rest of the figure.
Oh, you mean the this image right here?
Yeah.
Mm,
Is it a visualization of your nanowire? Of your model that you described? Wet right?
yeah, this seems like that, and I mean is this graph here just basically essentially a slice of that three-dimensional graph that we were talking about in David's talk earlier?
It's not a trick question. No tricks. Just would it be right to say that size of the nanowire model on the top and the range of the z-axis that you show on the bottom are the same? So the
Yes.
size of your nanowire goes from like minus 55 angstrom to plus 55 angstrom.
Yeah, that's right.
Okay, so it's same scale, same length scale. Then scientific question, not about protocol. Why the charge density spikes in either left or right? Why it is not homogeneously distributed over the whole nanowire?
Why it spikes over certain parts of the nanowire?
Yes.
Okay, I'm taking a guess here, but the spot where these spikes happen, are these essentially I'm guessing these are the parts of the nanowire where it's doped?
Yes. Excellent. Perfect. Great answer. Can you point where are the dopings on the image?
Alright, so the doping is essentially this colored things right here. This is a doping here, this is a doping here, this is a doping here, and right here.
So blue is sodium and purple is iodine.
Alright?
Right? Okay, good.
And you have the same thing right here for these two graphs. These are just basically different orbitals.
Wait. Let's. What is the connection between left and right parts of your slide?
So
where is this orbital, which is like the LUMO on the right side of the slide?
So this corresponds to this part right here.
Okay, and the HOMO, or HOMO -1, where it is on?
Right here.
Excellent, thank you.
Okay, so then next we're talking about the meaning and structure of the PPE and the PPH variables. PPH is the population of the electron hole, and then PPP is the population of the electron orbital. Just so clear that up. So then the population of the electron orbital, it's actually an array, which is essentially a one-dimensional matrix, and it has two indices. One index is
Matrix, not one dimension, two dimensional. Good.
okay. So then, yeah, the array has two indices. One index is a time step. The other index is the number of orbitals, and we're counting from the lowest unoccupied molecular orbital end up. And this array has the population of orbitals, and we're looking at the population of orbitals as they're changing in time. The PPH array is similar to this one right here, except this is the population of the actual electron hole. Like this, PPH has like two indices. The first index is the time step like this right here. The other index is the number of orbitals, and this time we're counting from the highest occupied molecular orbital and down. And then the data values in each record of this array, they're corresponding to the non-equilibrium population of the originally occupied orbitals. Okay, and then this is just the code we're using to make the graph for PPE and PPH. Waterfall PPE, we're basically graphing the population of electron orbitals. Waterfall PPH, we're graphing the population of the whole orbitals. And the bottom 3 lines of code right here is what we're essentially merging the populations of the electrons and holes into one variable. Okay, and then all 3 of these graphs right here is the population of the electron orbitals. This is the code we're using in Matlab to make these graphs. Waterfall, as we've discussed countless times, is the actual command we're using to make this. Where this axis and the numbers, we're specifying the range that this axis is displaying on in the lab. And then the X label, we're calling it time steps, as you can see on all 3 of these graphs. And then this graph is right here as an example. This graph right here is the population of the whole orbitals, waterfall PPH, and as David discussed in his previous talk, the x-axis right here is the time steps, y-axis is the specific orbital we're looking at, and then the z-axis right here is the actual population of the orbital itself. Same thing for this graph, except for this graph, we're looking at the whole orbitals, and the graphs are essentially the same. The x-axis, y-axis, z-axis are essentially the same.
What's the difference between top and bottom on the right? They're both for the holes, but something is different.
Okay, I think these are the same graphs, but the y-axis, there's less of a range here than it is here. So here, the y-axis is kind of smushed together. There's a greater range here on the y-axis, and here, as far as the y-axis goes, we're zooming in a little bit.
And how does the index of most populated orbital changes in the top and bottom? So in the top, you originally have number 6 has population 1, and at the end, orbital number 1 has largest population, right? What is on the bottom?
Okay. So the bottom is essentially the same thing is happening for these orbitals. This is 0, and then it climbs back up to 1, and then we see the same thing happening on this graph right here.
So counting of orbitals in the different direction, right?
Mm-hmm.
So what David has introduced, the PPH, the largest number corresponds to orbital deeper in the valence band. But if we try to go to computation of observables, it can make confusion if you want to overlay it with energies, because it should be like a lower index if we are deeper, and then continuously increasing as we go through all orbitals. So in this lower panel, this HPP orbital, the running of index is alternated in the opposite direction to match natural count of the orbitals.
Isn't it like that in the other ones?
Huh?
Isn't it like that in the other ones?
It is the same data, but they are represented in a different way. Like -5 is 96 here. Then we go down into the index. We go to the HOMO -4, and here this HOMO -4 we actually go up. It will be 97. So the counting of index of orbitals goes in the opposite direction. You can label axis as I or HOMO -I.
Oh,
Just mirror reflection.
that's what I figured it was, because it looks like the hole is gaining energy. It goes from top of the valence band down to something.
It's just mirroring of the index counting.
Okay.
Okay, next we have here is more graphs. So like the previous graph, waterfall PPE is the population of the electron orbitals, PPH is the population of the whole orbitals, and like the same thing in the last slide, we're merging all of this together into one array, and then this graph right here, x-axis is the time steps. Here is the orbital index. So this is essentially a slice of that three-dimensional graph we saw in the previous slide. Okay, and then this line of code here, we have density distribution as a function of space. So this is all the Matlab code we're using to make these graphs. This is a similar graph to the graph we had 2 slides ago. X-axis right here is the time steps. And then a little bit of a difference here. This axis is the angstrom, so then interatomic distance. And then this graph is just telling us how the energy changes with both distance and time. And as you can see, these spikes right here, they correspond to the doping. So these colored things you see here, that's where the nanowires were doped, and these energy spikes correspond to where the nanowire was doped. Same thing for this nanowire right here. Okay, this is a slightly different graph. This is a one-dimensional density distribution as a function of space, and then a one-dimensional density distribution as a function of space and time. So y-axis is distance in angstroms, and x-axis is the time, and then this is just showing once again how the energy is changing with distance and time, and once again
Not energy. Position or spatial localization, right?
So then this is telling us how distance is changing with time.
Most probable localization of electron changes in time.
Okay. Yeah, most probable localization of electron changes, how that's changing in time.
Hmm?
Okay. Yeah, so that's what this graph is showing. Once again, these colors are the doping. And then this is just some additional code right here. This is the expectation value of position of excited electron and hole, where we're basically like putting all that data into these variables right here. And then this last 3 lines of code here is we're plotting everything, and then you get this graph to your left. All right, the next thing I'm going to talk about is the dipole variable. So the dipole variable is an array or a vector with just one index, and then this index refers to the number of that specific orbital which it's talking about. The data record number I in the dipole array, that's basically the expectation value of the z coordinate for the number I. So then this dipole, that, as you can see here, this is basic drag notation for those of you who've taken quantum mechanics. So this is the expectation value for the dipole, which I'm sure you guys have seen countless times. And then this int dz integrating with respect to dz, the probability density squared times the position z. So that's basically, this dipole is essentially the expectation value of z in the ith orbital. Yes?
So you say that the dipole is it's a 1D vector. Is each element of that vector just the dipole moment or a different I?
Yeah.
Z projection of a dipole moment, because we are interested in voltage and current only in z direction.
And are you taking into account off diagonal stuff or just I in that documentation?
Just okay, and then yeah, this line of code is the expectation value of the position of the excited electron bolt, excited electron or hole. This is the Matlab code you'd use to find the expectation value, and then this is the expectation value of the dipole. Okay, next I'm going to talk about the AVE-DIP variable. It's an array with each index indicating the time step. It contains the value of the electrostatic dipole at each point in time. Each value of the dipole array is multiplied by the appropriate value of the PPE or PPH array at each point in time. So then the partial contribution of each orbital to the formation of the dipole at each point in time. And then all partial contributions of each orbital are basically summed together, and then they provide a value of the AVE-DIP array. And then this is just the sum of the dipole at the highest occupied molecular orbital plus the lowest unoccupied molecular orbital. And then this is the Matlab code you would use to get first the excitation value of the dipole. That's what these first 2 lines are. And then this is the dimensionless dipole time increment, and then the time integration, and then this the line here is the rate of the dipole change.
So it's the same thing as David was introducing for Hutker rotation energy, right? Mm-hmm.
Okay, and then here we're plotting the position with respect to time. Red is the position of the electron, green is the position of the hole, and then blue is the position of the dipole. Something I think is worth pointing out is that the red graph is essentially the inverse of the green graph, which is to be expected because red is the position of the electron and green is the position of a hole, hole being the absence of electron. So it makes sense that these 2 graphs are essentially like an inverse of each other. They're essentially like mirror images of each other around the
Here it could be a coincidence. It's not a general theorem.
Okay.
Electron and hole could very likely be at the same place,
All right.
as you have seen in the talks by London.
Okay.
So they do not need to be mirror reflection.
Okay.
It's maybe your system is symmetrically doped and there is some symmetry, but it is not general.
Okay.
Oh, can you go back this one? Yes. No. Yeah.
Okay. Last slide here. This is basically a graph of a dipole and how it's changing the time. This solid line here, we're basically this is essentially like fitting it. That's basically like a rough fitting, and then this is the Matlab code we use to generate this graph.
So the goal is to make some tricks for these two lines to coincide.
Okay.
Find such fitting that would the solid line will literally follow the dashed line, right?
All right. And then here, this is essentially like all the Matlab code I talked about in this talk. I've condensed it into just one page. So if you guys want to, you can just download this PowerPoint and go to this slide and just copy paste each of the Matlab code into your Matlab script. And that's essentially my first talk. Any questions?
Okay, then thank you, Kevin.